I'm good, Hojam.
Okay, everything is good, right?
Yes.
Good, good. Are you also taking 208 Dynamics, or this is the only course you are taking with me?
This is the only course, Hojam.
Okay. If you need any office hours, please let me know. Okay. We still have 5 minutes. So we will wait for our students to come. So technically, this is the problem we have today. Very nice and beautiful problem. How many students agree? Okay. So this is also in the homework, by the way, as one of the students pointed out today. And then I have nice and beautiful. Okay. Yes, no. Okay. Okay. The question says, if an axial force of 200 kilonewton is applied to the assembly, you can put a compressive or tensile, I don't know. It's entirely up to you. Hang on. 200 kilonewton. Is applied to the assembly by means of rigid end plates. Determine the normal stress in the aluminum shell. The second part of the question is the corresponding deformation of the assembly. So we have delta of assembly Salam, how are you? Good, good. Good morning. Good to see you. Okay, why don't all of you take these pages with you for you, please? Hello, how are you? It can be compressive or tensile, whatever. Okay, so let me repeat the question. An axial force of 200 kilonewton is applied to the assembly shown by means of rigid end plates. Determine the normal stress in the aluminum shell, the corresponding deformation of the assembly. So how can we start the problem? We still have 1 minute. Okay, dimensions, I think I did not write. let me write for our online students. The inner dia is 25 millimeter. The length of this fellow is 300 millimeter. The outer dia is 60 millimeter, correct? The brass core has elastic modulus of 105 gigapascals, and the aluminium shell has elastic modulus of 70 gigapascals. Okay, 6, 5, 4, 3, 2, 1. Hello, everyone. Welcome to another session of strength of materials. So our problem is that 200 kilonewton is applied to this assembly by means of rigid end plates. We have to determine the normal stress in the aluminum shell and the corresponding deformation of the assembly. So in order to tackle this problem, you have to understand that this problem is also, if we use the right wording, it is statically indeterminate. You have to utilize concepts of strength of materials if you want to crack this problem. So let me start this problem by saying we have, let's say, P equal to P of, let's say, aluminium plus P brass, right? And then I will say, because at the end of the day, when you are applying a load, please understand that you are applying the load by use of some rigid end plates, because all of you can say, are you applying the load on the brass or are you applying the load at the aluminium? No. I will again read the wording. It says by means of rigid end plates. So you can assume that you have put some little disc at the end and another little disc at the end. You have kind of glued that disc. So at the end of the day, when you are putting a load, that load is transferred to aluminium and brass. Got it? Huh? Okay. Then I think all of you can realize that what we have to find is, we have to find normal stress in the aluminium shell. So I suppose it will be P of aluminium divided by A of aluminium. Now, in order to crack P aluminium, I need one more equation. And that's what I'm saying, that statics actually raised its hands and it is telling me that you need 206 concepts. So how can I come up with another equation?
The deformation in aluminum should be equal to deformation in brass.
Good. So he's right. So I will say that my second equation is delta of aluminium. Gentlemen, delta of aluminium is equal to delta of brass, and P L EA is equal to P brass, length of brass, over E of brass, A of brass. And I will take this liberty of writing quickly that the, hang on, this P is, I suppose, 200 kilonewton, right? So I will say P equal to 200 kilonewton. I need one more equation, and one of the students said, why don't you use this equation? So I will be using this as the second equation. So for those of you who just joined, you have that piece of paper in front of you, right? Now, I have already explained to the class that this is being subjected to load by means of rigid end plates. That means there's some little piece that you have glued at the end. So at the end of the day, the load is distributed to brass and aluminum. Okay, area of aluminum. Anyone? And anyone who can please tell me area of brass? I'm definitely not doing it. You need to help me.
That's 4.9,
Huh,
10 to the power minus 2.
good. 4.9 into 4.9 into 10 power
Minus 2.
meter power 2. Okay, an area of aluminum is okay 2.336. Can you please confirm? Okay. Okay, now all you have to do is finish the problem. So I will have P aluminum from here over PB. Hello. That page, P aluminum over PB is equal to, you need to tell me this, this box, okay, quickly. And then finally, I will write from here P equal to, that is 200 into 1000 Newton is equal to P of aluminum plus P of aluminum divided by, you have to again tell me this little box, and P aluminum comes out to be some beautiful value, and stress of aluminum comes out to be P aluminum over A aluminum. I know that all of you are like, why are we going at sonic speeds? But we already did this topic. I am revisiting it. And then this value comes out to be, you have to give me the value in meter. We are stopping here for 5 minutes. Do it. Give me the value. For those of you who have just arrived, rigid end plates are at the end. I did not show that on the diagram. Kind of caps. So they are glued at the end, and then on those glued caps, I'm applying a load. So that load actually transfers to the aluminum and brass. So it's like somebody puts pressure here right now, or there are 2-3 guys who are sitting here and they are like taking that load together. The one who is stronger will end up getting a bigger chunk of the applied load. Is this a statically indeterminate problem? Oh, absolutely. I need 206 concepts to crack this.
So can I get the answer?
Give me the values.
Force experienced by brass is 47.9.
Hey, wait. What did you say?
47.9
For what?
for brass.
Force?
Yes.
Give me for aluminum.
151.9.
Very good. He got the answer. So anyone else who wants to do it? 152 is in my notes. 152.077. So I will say P aluminium is sorry. I will use a 152.077 Newton. Sorry, kilonewton. Can you please give me the box? This box?
Orange one, sir?
Yes, P aluminium or P brass?
3.17.
Very good. 3.1733. This is a ratio. Then 3.1733. What about delta? You need to give me P AL over EAL or you can give me PB over EB. Both of them will give me the same answer. Nobody is trying. Since nobody is trying, either this problem is too easy or too difficult. I will go with the former one, right? I think it's easy. Okay, I think. Okay, 10, 9, 7, 6, 5, 4, 3, 2, 1. Any questions? Okay.
So force will not distribute equally.
Of course not. Let's just imagine if two guys are standing here, two persons, and another person comes to fight, let's say. The one who has more strength will be able to defend more, right? So between brass and aluminium, one of them has the capacity to take more load. Good. So I keep on emphasizing there is a rigid end plate at the end. So there is a cap. 1 minute. There is a cap here. Let me put a purple color like this. On that cap, the load is being applied. Okay. And same story for. Did you do it, please? Delta? Give me the answer. We have been waiting. No?
The 105, which one?
Huh?
The
Delta.
for the E, E aluminium.
The E aluminium is. Sorry. Okay, E aluminium. Oh, yeah, the brass has 105.
Okay.
Brass is 105. And aluminium is 170. Millimeter? Good. 2.79 millimeter. Thank you. I don't have the answer. Okay. 10, 9, 7, 4, 3, 2, 1. Should I go back? We had a student who was writing. Should I proceed? Okay. Okay, everyone. Can you please turn the page quickly? So the next question is, we have oh, come on. Where is the question? Yes, the question says I have a brass bolt, and this brass bolt is nice and beautiful like this. I know most of you are like, these are so easy problems. Why are you even doing it? You will understand the reason now. I'm telling you, trust me, you will understand the reason why I'm doing this. problems now. So nice and beautiful brass bolt, and the brass bolt, I will put a nice and beautiful imaginary line like this. Then I will put a nice and beautiful, oh, come on. This is, these drawings sometimes take time. Okay, and then I have a beautiful nut. Okay, and then the same story goes here. Oh, come on. We need the same blue color, right? By the way, why don't you start solving this problem? At least our in-class students, they have the problem in front of them. So why don't you solve it? And why don't you tell me whether this is a statically indeterminate problem or not? Okay. Done. And now I have a brass bolt, elastic modulus 15 into 10 power 6 pound per square inch of 3 by 8 inch diameter is fitted inside a steel tube. Wow, there is a steel tube. So let me use a nice pink color for steel tube. That's nice. Okay, now you have to understand that this is a circular section and you are looking at the side view, right? Sectional view. Okay. Oh, come on, it's not even symmetric. I wish I had made this drawing a little early. Okay, now you can quickly color it and then I will proceed. So what about our online students? Are you following this? Then I have done. Now I will, for the brass, nice and beautiful orange. Come on, done. Okay. The problem says, again, I have a nice and beautiful nut. Let's say till here. Nut, and this goes through like this. Thank goodness. Okay, we have threads. This whole thing is going. Of course, let me put imaginary here. Okay, and I will just try to be sure that our students don't get confused. Thanks for your patience. Okay, now the question says that EB equal to, we have to go at sonic speeds now. EB equal to 15 into 10 power 6 pound per square inch, and the brass has a dia of 3 by 8 inches, is fitted inside a steel tube of ES equal to 29 into 10 power 6. Outer dia of this is 7 by 8 inch outer diameter, and it has a wall thickness of 1 by 8 inches. Okay. After the nut has been fit snugly, it is tightened a 1/4 full turn. 1/4 turn. Knowing that the bolt is single threaded with a 0.1 inch pitch, determine the normal stress in the bolt and the tube. Normal stress in the bolt and the tube.
There won't be needing the force.
Just hang on for a second, please. Bolt is brass. So this is brass. So brass and bolt are the same things for me. And tube is this one, TUBE. 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 Yes, please. What is the question?
Won't be needing the force. That the bolt is applying.
No, because deflection is given to you. You will not be needing the force. Okay, so for how to solve this question? In order to solve this question, we will start doing. Okay, we will say that solution we have deflection given to us as 1/4.1 equal to 0.025 inches. And that's it. Now you can solve the question. Deflection is given to us. It says, if you read the question, it says,
Yes, 1/4.
knowing that the bolt is single threaded with a 0.1 inch pitch. So this means if you turn it one time, it will travel 0.1 inches. After the nut has been fit snugly, it is tightened a 1/4 full turn. 1/4 means 1/4. Full turn means if it turns one complete, it turns one complete time, there will be a movement of 0.1 inches. So 1/4 means delta will be 1/4.1, that is 0.025 inches. Okay. Now, hang on, everyone. So follow me. This is not easy. So for example, this is a statically indeterminate problem, right? Just tell me what will be the equation of deflection. So how are you relating the bolt and the tube?
Both should have the same deflection.
No, this is why I am doing this problem. This is a little confusing. So please understand one thing, that when you are trying to tighten this one, what will happen? When there is a hole, right? For sure, this is going through it. So when you tighten, what will happen is that this whole chunk wants to go like this, right? So just imagine you're tightening it, right? When this whole chunk is going in that direction, this, for example, will not follow the same because there is a hole. So when you are tightening it, okay, probably it will go in this direction. Whatever the case might be, this and this will not deflect the same quantity. Are you getting my point? It's very easy to get confused. There is a hole. In the previous example, you were just putting the load like this. Yeah, okay, deflection is the same. This time when you are rotating it, this is hole. So this wants to go to like this when you're tightening. But at the same time, let's say this fellow wants to go here. So this and this will have different deflections. Okay.
Sir, but if we say that the bolt is applying the force on that blue bar, just like the disc you said, that there is a disc at the end, the bolt is now applying the force on the disc, so that all of the three members will experience that force now, I think.
So P bolt will be equal to P tube. Equal to P. Why don't you repeat the sentence one time?
I'm still confused why both of them are not experiencing the same effect.
Yeah, I will tell you why. Because in the previous, look here, there was a rigid plate, right?
Yeah.
And there was a rigid plate. So you were putting compression or tension, doesn't matter. At the end of the day, the whole chunk was experiencing the same deflection. But the story is not the same here. Here the problem is, if I had told you that this is a rigid plate, okay, that would have been a completely different problem and you are putting load. Right now what I'm telling you, it's a hole. So this fellow goes through it and you are turning this. When you're turning it, tightening it, what happens is that this whole plate with a hole in it wants to, let's say, go towards left. But when you're tightening this whole chunk, that actually now you can even see it's a hole, and there is also a hole and it goes right through it. When you're tightening it, this whole chunk wants to go towards right. So you can just imagine that these cannot have the same deflection now because of the fact that there is a hole. Okay, no? Yes? Okay.
Can we say like that this bolt, because it's coming outwards from the right hand side?
Even from the left hand side?
Yeah, from the left hand side, so it's not going to have deflections. Or is it going to?
No. You have not put it inside some wall. It's just, you are just tightening it. So the deflection is not zero. Okay. Now on that note, P bolt equal to P tube equal to P, because at the end of the day, the force experienced by them is the same. And yeah, the question is a game over. We have a steel tube equal to, you have to give me the value. Then a brass bolt, you have to give me the value. What happened? Chat message. So there are no normal stress on the bolt. Why? P bolt equal to P tube equal to P. Why not? The whole thing is not, let's say, floating in the air. At the end of the day, this is still in static equilibrium. Then we have a, we will have to find, let's say, delta bolt. Again, this is brass bolt equal to PB bolt over L. I suppose L is the same. Did I give you the value of L length or not? Length is 12 inches. Sorry for not specifying for our online students. Over E bolt, AB bolt. You will give me this value, which I don't think we have. Then we have steel equal to, okay, we will have PS. Oh, I apologize. I think this is steel tube. Why am I writing? Sorry, steel tube. And this is steel tube. So we have S tube equal to S tube, LS tube over ES tube, AS tube, PL over EA.
For total deflection, we set that 0.025.
Sorry?
For the total deflection, we set that 0.025, right?
Huh. Yes.
This deflection value, I think it will equals to the steel tube deflection. Because
No, it will be, I will tell you, it will be delta equal to, so let me just finish this, then we will talk. Delta equal to delta of bolt plus delta of tube.
then it doesn't go that far, so.
And you will replace this with a simple P,
Just goes in.
and you will replace this with a simple P because P is the same.
That's the deflection.
So we have this one. Okay. Okay. No, it's not clear.
Can I ask one question?
Yes. 10 questions. Why one?
Sir, when we tied the net,
Huh.
similarly, there is a plate with two bars. I'm saying, now the force is being applied on that two bars. Just like similarly in the previous question.
The problem is that it is a being applied on the blue thing, right? But the brass actually is going through it. So the blue thing will not put any load, let's say, on the brass one. Hole. There is a hole. When I'm tightening, you see, now let's say I'm putting a load here. You're getting my point. Putting a load like this and putting a load like this are two different things.
So how can we say that the force is equally divided?
That is a
That's the question.
good. His question is why the load is equal. Because when you are tightening it, right? When you are tightening, then the force with which this fellow wants to go outward is the same as the force that is acting here. We can think about it probably. His question is, but why force is equal? Force should be equal. Okay, we will think further. Okay, let me do this. Give me the value, and then also give me this value. Think further. Just give me the values first. Okay, use the calculator. So for example, when you are typing this thing, it says that it has a pitch of 0.1. That means when you turn it one time, there will be a movement of 0.1 inches. And then the author says that you are turning 1/4. So if you are tightening that nut quarter,
It also goes to one.
Aren't they all connected? This whole thing, or?
this is first of all, this is hollow. So there is a hollow steel. In that hollow circular, there is a brass. This is brass that goes right. There is a hole. You can see that the brass is through the hole goes right. Whereas steel of course is just connected to this fellow. So when you are tightening it, this brass wants to go through this hole, right? So there is a hole, but this steel cannot escape through a hole. There is a plate here. So when you turn it quarter of a circle, it will a delta deflection will happen 1/4 quarter of 0.1 inches. Because when you have a pitch of 0.1 inches, this means with one turn, this fellow can move 0.1 inches with one turn. But the question says that there is 1/4 full turn. So 0.25 or 1/4 of 0.1 inches. There will be a deflection. Yes, sir.
So we just make the brass equal to the friction and brass equal to on the brass.
Good. So your answer is in the form of PV. Good.
I mean, not materials. This plate can compress this steel, right?
Yes.
And also, because not is strained, this steel plate acts like a wall. This breast bolt will be in pressure, right?
Yeah.
So because of that, we couldn't say it's just tube deflection.
Exactly.
Because when the wall comes like this, also the wall comes like this, and there is a not
Good. Yeah,
because of
exactly.
that.
Very nice. Good. Okay, why don't you give me the answer? No. Yes. Anyone? Okay, so we have delta bolt is equal to 7.24 into 10 power minus 6 P, and then this fellow is 1.40 into 10 power minus 6 P. Okay. So all you have to do is now area of tube is 0.29452 0.29452 inch square, and area of bolt is 0.11045 inch square, and finally yes, we will say P not P, we will say delta is equal to delta bolt plus delta tube, and this will be PL, it is equal to delta bolt plus delta tube. So delta is 0.025 equal to 7.2431, one of the students told me, into 10 power minus 6 P, plus I will use a different color for tube, that is, one of the students told me 1.4050 into 10 power minus 6 P. So now I have one equation, one known unknown. Let me use purple color, and P comes out to be 2.8908 into 10 power 3 pound force. If you want to put a subscript F here for pound force, it's good. And last but not least, stress of bolt comes out to be, it's brass bolt, force divided by brass bolt, which is equal to 8908 into 10 power 3 pound divided by area of bolt, which is 0.11045. What happened?
I get it right.
Okay. Then this is inch square, and we get 26.2 kilo pound per square inch. And stress of tube is steel tube is equal to P of area steel tube, which is equal to okay, it is equal to minus P. So this is minus because the steel tube is in compression, divided by area steel tube. You put the value of negative here and you get minus 9.82 kilo pound per square inch. Because when you are tightening it, the brass wants to come like this, but the steel tube will be under compression.
So it's in compression, we said it's minus.
Yes.
Minus.
Oh, yes. Yes. Because this is hollow and its thickness is given to me. So I will do, first I will find radius and I will subtract the thickness to get the radius of this fellow. And then I know the radius of this, and I know that the area is pi r2 square minus r1 square. So in order to get the radius, you will have to subtract. In order to get the radius of this, you have to subtract the thickness from the other. Yes, it's correct.
I want to.
So the actual,
Yes.
so the actual answer for the radius of the seal, right, is going to be alpha minus 1. Is that how we found the area of the tube?
The area of the steel tube. We got it pi r2 square minus r1 square. So outer radius is known. Inner radius you have to find. Inner radius is the outer radius minus the thickness. Yes. Yeah. So at the end of the day, you say.
Okay, there we should say.
So then at the end, when you are doing this, you instead of this substitute P, instead of this,
And you find the ratio and you, okay.
at the end, there is a PL over EA here, there is a PL over EA there. I added them. Hang on. I added them and I equated it to 0.25. I added them and I equated it to 0.25. Look at there in the red. Delta 0.025 and
Also, we say the forces are same because we're not making the force, there's also the action forces. And
yeah,
the
exactly. That's why the P is the same. You're right. Okay, is this clear? Yes, no?
The second, I think in A2.
How to find the A2 area? Oh, okay. So we have area of, let me use a different color. Steel tube equal to pi r2 square minus r1 square of tube pi. So we have dia of the tube is 7 by 8 inches. And then I have thickness is 1 by 8. So I will do a 7 by 16 minus 1 by 8. No, there is no problem. I'm pretty sure. So for example, if this is your and this is this, so you will subtract from this chunk, this chunk.
Okay, I get it. I think we like that.
1 by 18 or 1 by 8? Or 16?
It's 1 by 8. This one, 1 by 8. Sorry. Done? Whose pen is this? Yours? Hang on. Okay.
Can you show the previous problem as well?
Yes. Okay. Where did I put my mobile?
Here.
No, it's not good. Okay. Now. So 5 minutes. So let us say goodbye by just summarizing a critical concept. I have already explained concept, application 2.2. This is again from your textbook. It is again, you have this fellow, and you have again, this is in the form of circular. Let's say you look at the side view. I mean, so this is like this. No, it's 3 minutes. So I will take a lot of time. Hang on. Let me go to the screen. Let me open. This is your. Let me pause the recording. Please remind me to resume the recording. Okay. Yes. Okay. I resumed it. So. Have concept application 2.2. I wanted to talk about. Oh, hang on, come on. Finding things is also hard in this book. Yeah, this one. So our online students can see, right? Everyone, quick. Look, this is concept application 2.2. You have this circular object, right? This is a rigid plate. I hope you can see the rigid plate, right? This one. So now when you're putting the load, it is being taken by both the tube and there is a rod inside, and this is a rigid plate. So if I ask you for this static indeterminate problem, you will tell me that one equation comes from the fact that the change in length of the tube is equal to the change in length of the rod. So just by the statics P equal to P1 plus P2 will not be sufficient. So one equation will come from here. The second will come from P1 L1 over A1 E1 equal to P2 L2 over A2 E2. Unfortunately, the lengths of these fellows are same. So you will equate them and you will get P1 in the form of this fellow. And again, you can substitute here. So eventually you will get P1 and P2 in the form of beautiful expressions. And now all you have to do is do whatever you want. So for example, now that I have got my P1 in the form of P and P2 in the form of P, this means I have calculated P1 and P2. Now I can find the stresses if I want, or do whatever I want. But so two equations, this one and this one, and two unknowns that is P1 and P2. So again, this is the concept that we did today. Okay, any questions?
How did you write P1 and P2 in terms of P?
Sorry?
How did you write P1 and P2 in terms of P? From P?
Yeah, so what we did is we equated these two fellows. So P1 over A1 even equal to P2 over A2 E2. Then I will take all these terms on the right hand side. So P1 will be equal to P2 over A2 E2 multiplied by A1 E1. Then I will take this big ginormous chunk and I will substitute here. So this P1 will be in the form of P2. So P2 will be on one side and P on the other side. So P2 can be written in the form of P, P1 can be written in the form of P. So P1 can be written in the form of P and P2 can be written in the form of P. Okay, thank you so much. Dogu Khan, do you have any questions? No, yes.
No, hocam.
Okay.
It's clear.